Alright, so uniform motion problems are related to the formula D equals RT, where D is distance traveled, R is the rate, or speed is another name for that, and T is time. So get a basic idea of what this, how this formula works. Let's say we are looking at the situation where a car travels for this car is driving 72 miles per hour for 90 minutes. We want to know how far the car traveled. So we use our formula, distance equals rate times time. We fill in our numbers. Our rate is 72 miles per hour, and our time is 1.5. Why did I put 1.5 instead of 90? Well, notice our rate is in miles per hour, not miles per minute. So you have to keep all your units the same. So since I'm talking about miles per hour, I should change minutes into hours. So there's 60 minutes in an hour. 90 divided by 60 is 1.5 hours. That's going to be very important. You never want to work with different units of time, or so that things work out correctly. And then you multiply those. 108 miles is how far that car would drive. So one of the hardest things about uniform motion problems is knowing exactly what kind of situation you're dealing with. So in some cases you're going to be adding two distances together and getting a total distance. That may be a situation where two objects start apart from each other and they move towards each other. That would be a situation where you'd add the two distances and get some total distance. You might also have a situation where they start together and they move away from each other. So again, you add how far the first one goes plus how far the second one goes. That would equal some total distance. And then you might also have a situation where one object travels part of a trip at one speed and then the second part of the trip at a different speed. And so then you'd add those two distances together to get some total distance for the entire trip. But that's not the only way we can look at objects. We can also look at them, the distance of the first one equals the distance from the second one. And occasionally you might add on some kind of adjustment value here that, we want one to have get 5 miles ahead, or maybe they had a 5 mile head start, and so that's how we would equal their distances. So you might have one where one's going faster than the other. They start at the same place, same time, and so you add on, maybe we want to know when's the first one 10 miles ahead, so we'll add 10 to the distance the second one travels so that their distances can be equal. We'll also have one that had a head start already. So maybe you add 5, the second one has a 5 mile head start, you add 5 on there. A lot of times this adjustment though will be calculated into like the time, when we'll have start an hour earlier. And so we'll just say D1 equals D2 and we'll just put that extra hour into the formula. The third kind of situation like this is where you have one object but it goes somewhere and comes back. So those two distances would be the same because, start, end, start, same distance traveled, and we'd set those two equal to each other. So I'm going to go over a few of these kind of situations of examples that you might see, but realize this is just kind of a representation of all the possibilities that could occur. And there may be more that I didn't think of on this kind of listing here. So just, if you have a... Alright, so let's look at this problem. Two cyclists start at 1 p.m. from opposite ends of a 54-mile racetrack. The average speed of the first cyclist is 17 miles per hour. The average speed of the second cyclist is 19 miles per hour. At what time will the two cyclists meet? So we know how fast each one is going. We know how far they started off apart. We don't know how long they're traveling. We don't know their times. First thing we want to do is figure out what kind of relationship we're looking at here. And this is one where we're starting apart and we're going to move towards each other. So we're going to add the distances to get some total distance. Now we don't know the distances each one traveled directly, but we know from the formula distance equals rate times time. So if we want to figure out the distance for the first one, we're going to take its rate times its time. The distance from the second one is its rate times its time. And that'll give us the two distances, and we can add that and get the total distance. We know how fast the first one's going. We don't know its time, so we're going to call that x. And we know the speed of the second one, that's 19. We're going to call its time x also because we were told the two cyclists both started at 1 p.m. So the time they travel, since they start at the same time and obviously they meet at the same time, their travel time is exactly the same. So we're going to figure out this, and this is going to give us how long it took them to meet. So just cleaning this up a little, dropping the parentheses. Combine like terms, 17x, 19x gives us 36x. Divide both sides by the coefficient, 36, and we get x equals 1.5. So what does this tell us? This tells us it took them 1.5 hours to meet. That is not the question, though. The question is at what time do they meet? And what that's talking about is what time of day. So remember, they started at 1 p.m. If you add on an extra hour and a half, you're now at 2:30 p.m. is when they meet. So be careful. You're actually answering the question they're asking. You may have to find something first before you can answer that. But make sure your final answer is what they asked. They wanted us to know what time they met. They met at 2:30. Alright, let's look at this problem. A cyclist traveling at 18 miles per hour overtakes an inline skater who is traveling at 10 miles per hour and had a half-hour head start. How far from the starting point does the cyclist overtake the inline skater? So what kind of situation? They're going the same way, and the second one had a head start, had some kind of adjustment that got them up ahead of there. So we're looking at distance 1 equals distance 2 plus some adjustment maybe. That adjustment's going to be figured into the time because we're told they have a half-hour head start. So we'll just do rate 1 time 1 equals rate 2 times 2. So we know how fast the first one's going. We don't know how long it's going. So we're going to call that x. We know how fast the second one's going. And we know it's going half an hour. It went half an hour longer than the first one. So we're going to add 0.5 to x for its time. We don't want to call them both the same. That would mean they were the same amount of time. And we know the first one, or the second one, the inline skater, was going for a little bit longer time. So now we're going to solve this equation, distribute 10 times x, 10 times 0.5, so they only have x's on one side, so I'm going to subtract 10x from both sides, get rid of the coefficient of 8, divide both sides by 8, and I get 0.625. So remember, x represented the time of the time of the cyclist, how long it took them to catch the inline skater. But that's not what the question asks. The question asks, how far did they go? So remember, distance equals rate times time. If they're going 18 miles per hour for 0.625 hours, they traveled 11.25 miles before they caught the inline skater. Two hikers start from the same point, hike in opposite directions around a lake whose shoreline is 13 miles long. One hiker walks 0.5 miles per hour faster than the other hiker. How fast did each hiker walk if they met in 2 hours? So, even though this isn't wrapped around a thing, we're just looking at, if you think about the perimeter is, stretching the perimeter out into a line, it would be this kind of situation. We want to know when they've covered a distance of 13 miles together. So distance 1 plus distance 2 equals the total distance. And again, rate 1 time, distance is rate times time, rate times time. So there we go. Let's see, what do we know? We know that we don't know how fast either one's walking, but we do know one of them is faster than the other, half a mile per hour faster than the other. And we do know their times. They started together and they met 2 hours later. So we're going to fill those in. I'm going to say the first hiker is going to walk at a speed of x, which means the second one's going x plus 0.5, half a mile per hour faster than the first one. Again, both of them walked for 2 hours before they met up. And they walked the entire circumference of the lake, so they met each other. They walked an entire distance together of 13 miles. So cleaning this up, distribute that 2 times x is 2x, 2 times 0.5 is 1. Combine like terms, 2x plus 2x is 4x. And now solve this for x. So get rid of the constant term, subtract 1 from both sides. Get rid of the coefficient, divide both sides by 4, and you get x. And that's how fast one of them is going, and the other one's going half a mile per hour faster, so 3.5 miles per hour.